The computer graphics field is filled with applications that require the setting of tricky parameters. In many cases, the models are complex and the parameters unintuitive for non-experts. We present a machine learning method for setting parameters for a procedural fluid animation system. It uses a gallery of animations and collects user feedback to find a set of parameters the user likes. We apply our method to generating smoke animation, which drives a set of passive marker particles through a procedurally generated velocity field. This velocity field is generated by taking the curl of a vector-valued potential function. There are two main components to this potential field: the contribution due to a set of vortex rings and a spatially varying noise function. In total, the model requires the tuning of between 6 and 12 real-valued parameters. Generating high-quality renderings is expensive. Fortunately, we can quickly generate low-resolution animations in seconds. This allows the user to find the desired settings and then generate a high-quality animation clip. Different parameter settings can be used to produce a variety of distinctive animations. However, finding the right values to generate a specific animation is difficult, especially for non-experts. Our solution is to use techniques from machine learning to present the user with an animation gallery. At each iteration of the gallery, the user is shown 4 animations, which they rate by indicating preference for animations that look more like their target. By using preferences, we reduce the cognitive effort required to evaluate the animations, though users can also directly assign numerical ratings to the animations if desired. When the user completes the task of entering preference feedback, the model of the user's interest is updated, and 4 new sets of parameters are automatically selected. In selecting the examples, the system automatically evaluates the trade-off between 2 competing goals: trying to offer improvement on the animations the user is known to like, and exploring regions of the parameter space for which the user's preference is unknown. It is not our intention to supplant user expertise, but to use it more efficiently. In reality, users are unlikely to come to the system with absolutely no idea of what parameter values they are looking for. Even novices, after looking at a few samples, can quickly realize that certain parameter values are unsuitable. Furthermore, even when using feedback efficiently, exploring the entirety of a high-dimensional space to a reasonable sample density is a tedious activity. Our interface allows users to restrict the ranges of any or all of the parameters or fix them at a specific value. These techniques work well for a few parameters, but as the number of free parameters increases, the space simply becomes too big and empty to explore. However, we have an important resource available to us: all the previous users of the system. Even though the users may have been looking for entirely different types of animations, they are exploring the same space, and we can aggregate their behavior to learn priors on our model. The highly varying parameters are fit with priors on their width, which will drive exploration of nearby values more than slowly varying ones. We use a particle filter to track the most likely values of these hyperparameters. We can also put a prior on the valuation function. No matter what a user is searching for, some ranges of the parameters may simply never produce good animations. Certain settings might be good for some instances, but not others. If nothing is known about what the user is searching for, the system should initially avoid the parameter settings that rarely or never produce good examples, and instead start off with settings that previous users have rated highly. We learn this prior with a radial basis function network trained on data from previous sessions. When a new session begins, this prior is a valuable source of information and helps direct the examples for the gallery. As more information is added, the prior loses influence, and feedback from the user becomes the main source of information. The intent is to use popular settings when little is known about what the user is searching for, and use less popular ones when they seem to fit the user's task. We can update the priors after each use of the application or as frequently as desired. In essence, we have an application that is continuously learning from a variety of users performing a variety of tasks. The more it is used, the more accurate the priors become. It is even possible to adapt to different users or groups by using different priors, creating tools that are automatically personalized to different requirements.